Okay, so the second law of thermodynamics says heat flows naturally from a blank object to a blank object. What should that be?
Wait, when did you hand the cold?
Okay, hot to cold. I just handed it out. So just get one of those. Okay. From a hot object to a cold object. Okay. And not the other way around. Okay. The only way you can go from a cold object to a hot object is in, for example, a refrigerator. You have to do what in order to transfer energy from the cold region to the warm region? You have to do work. That's the only way you can do that. Okay? All right. Here's how a heat engine works, right? We take heat from what's called just a heat source, okay? It brings heat into the system, and then it does work. Because not all systems are work perfectly, we always lose some heat, okay, to what we call the heat sink. All right? So, generally speaking, the equation for heat engines is equal to this. So, the heat that you put in is equal to the work done plus any heat that you lose. Right? Yeah.
Why do you have to lose heat?
Because you always lose heat. I mean, just like, in your car, there's always friction. Okay, we can't. There's no way to, no matter how advanced we get, there's no way we'll ever be able to transfer all of that energy to heat. I mean, from heat energy into mechanical energy. Okay. All right. Now, the efficiency equations. This is the efficiency equation for any engine. Okay. It essentially says that the efficiency is equal to the work done divided by the heat in. Okay. So if it's completely efficient, which is impossible, right? This value would be equal to what? Would be equal to 1. Okay. Now, when they tell you it's an ideal engine, you can use this equation there. Or if they use any of these words, reversible. So write these down. If they use reversible, Carnot, which is a type of engine, okay, then this is the equation you will use, okay, for what's called an ideal engine. This can be rewritten like this. QH minus QC over QH. Now, the AP test hasn't had too many of these questions lately, so we've been sort of ignoring it. And if they do come up, there's such a small part of the test question. T is the temperature. So the temperature, for example, in this heat source, okay, yeah, so this would be the TH here and the T cold here. Yes. Yes. It depends on what's given to you. Okay? Now, because of this, we can also write ratios in this particular heat engine. We could write QC.
Wait, is that Carnot or?
Carnot. Carnot is French. So QC over TC is equal to QH over TH. Okay? So if a problem, wants you to convert from temperatures to heat, if it gives you 3 of the 4 of these values, you can find the 4th. Okay? What's that? It just comes from deriving this equation up here. Okay, this kind of problems only come up once on the AP test, on the free response part, and they've been really de-emphasizing it lately, so we're not going to make a big deal about this. Okay. What's that? No. I don't know. It's just like congratulations and congrats, right? Okay. So entropy. Entropy, you just need to know a few things about it, okay? Entropy is a measure of disorder. Okay. Entropy naturally increases. So that means that things naturally get more what? Exactly. Things get more disorderly. So if you take your bedroom, for example, right, it takes more energy to clean it up than it takes for it to fall apart. All right, for the things to get messed up. Okay? All right. So entropy cannot decrease. Okay. Unless work is done to the system. In other words, things can't get more orderly on their own. All right? Entropy increases when the kinetic energy increases or if the volume increases for the same system. So these are just some facts that you need to know about entropy. All right? Okay. So basically, these are just some kind of equations that we're just kind of throwing in to solve some heat engine problems. Yeah?
How would increasing volume increase the entropy?
Okay. Remember how work has got to be... Okay, so let me hit pause on here. All right, so another thing that we need to know, okay, is this special heat engine, the Carnot engine. Okay, now I've given you the entire setup for it, so you really don't need to fill anything in. The main thing about the Carnot engine is that it's based off of all things we already know. Okay? The Carnot engine, from 1 to 2, when we go from state 1 to state 2, that's an isothermal expansion. So the temperature is constant, and since delta U is equal to 0, delta Q will equal negative delta W. Okay? So that means the heat in equals the work done by the system. All right? And then from state 2 to state 3, you need to know that's an adiabatic expansion. So basically the Carnot engine, it just helps emphasize the things that you already know. Okay? And from 2 to 3, there's no heat flow, and since delta Q is equal to 0, then negative delta U equals negative delta W. The work done by the system equals the decrease in the internal energy. Right? From 3 to 4, that's isothermal compression, where the temperature is constant. And since delta U is equal to 0, then negative delta Q is equal to positive delta W. Work done to the system equals the heat leaving the system.
Is that a cyclic process?
Yes, it's a cyclic process. Okay. And then from 4 to 1, adiabatic compression, again, there's no heat flow. And since delta Q equals 0, in this case, delta W equals delta U. Work done to the system equals the increase in internal energy. All right? And so because it's a cyclic system, when we go, for example, from 1 to 1, we know what's got to be true. Yeah, the change in internal energy has got to be equal to 0. All right? And that affects the first law as well. All right? Okay. So I didn't want to spend too much time on that.